This time we have more numbers. We've got 2, we've got an 8, and we've got a square root or a cube root of 2. Again, our goal is to get a single power on both sides with the same base. So looking at the numbers, we've got a 2, and an 8. I hope you can see that they fall into the column of 2s. So to start off with, I'm going to change the 8, put it in brackets, and change it to 2 cubed. Exponent laws. How do you change the cube root of 2 to an exponent? Do you remember what square roots are as exponents, cube roots, fourth roots? That you can write any square root or any radical as an exponent, as a fraction. You remember that? It's coming back to you a little bit. Do you know why it works? Okay? I'll give you a quick explanation of why it works. It's really quite nice. First of all, I am going to give you something easy to think about. Would you agree that the square root of x times the square root of x would just equal x? Because that would basically square your square root, and your square root would go away. And if I did it with cube roots, how many cube roots would I have to multiply together to get rid of it? Does it make sense? I'd have to multiply 3 of them to get rid of it. Okay? So now, what I'm going to do is I'm going to write this x on this side as x to the 1. And I'm going to change these by putting a fraction or a number inside of those blue squares. Now the number that I have to put inside of those blue squares has to be the same, because I have a square, I'm changing square root of x to something. What's your exponent law for multiplying if you have the same base? What do you do to the exponents? Add them. What's the only thing that I could add here that makes perfectly 1? And they have to be the same. Obviously, 0 plus 1 is 1, but then they're not the same. The only thing that I could add that's the same is a half and a half. So that's the reason that we can write the square root of x as x to the half. And it's the same reason we can write, if I have a third, plus a third, plus a third, I will get an x to the 1. Again, sometimes it's nice to see a reason why something works, because then your chances of remembering it are going to be better. So this is the reason I can change my cube root of 2 to 2 to the 1/3. What's my exponent law for multiplying with the same base? Multiplying with the same base, I can put it together as a single power by adding my exponents. And if I add those, I need a common denominator. So I'll change my 3 to 9 over 3, 9 over 3, plus 1 over 3 is 10 over 3. And now I've got a single power, so I can go, so x would have to equal 10 over 3. Like, right, when we put this together, again, think of something simple, because I see what you're wanting to do, right? 2 squared times 2 cubed. The answer is 2 to the 5. It's not 4 to the 5. You never multiply the 2 times 2 to make it 4. And why is it 2 to the 5? Well, 2 squared means 2 times 2, and 2 cubed means 2 times 2 times 2, and repeated multiplication, that is 1, 2, 3, 4, 5 2's all multiplied by each other. It's going to be 2 to the 5. It's not going to be 4 to the 5 because you don't have 4 multiplied together. Okay? But as soon as we go to fractions, it's amazing how our brain forgets rules. It's like here, it'd be like, oh, it makes total sense that I get 2 to the 5. But here, you see how you were tempted to make that a 4, right? You want to be like, oh, 2 times 2 is 4. I'm good at mental math. This unit is really good at testing your restraint, because you are good at mental math, but it will like tempt you to do mental math before you should. Or when you're not, in this case, not even allowed. So if we look at part B here, first of all, we see 125 and 625. On our powers chart, that happens in this column of powers of 5. So I'm going to change the 125 to a 5 cubed, and I'm going to change my square root to a 1/2, and I still have the 2x plus 1. Lots of brackets on this one. Equals, I'm going to change the 625 to 5 to the 4, and I'm going to change the cube root to 1/3. Power to a power is multiplying. I'm going to do this in 2 steps. First, I'm going to do this power to a power. And get 3/2. And I'm going to do this power to a power and get 4/3. Then I have a power to a power again. So I'm going to need to multiply these together and distribute. Is that his there? And now, since we have a power with the same base, we can circle and say, so the 3x plus 3/2 has to equal the 4/3. So let's solve for x by getting x on one side. How do we subtract fractions? We need a common denominator, so this will be 8/6 minus 9/6. And dividing by 3 is the same as multiplying by 1/3. So a lot of algebra was involved, and a lot of fraction work and exponent laws.
Do I have to circle like so before?
No, you don't have to circle it, right? At this point, this is just, the reason I write so is because we're not actually doing something mathematical. We're just doing an observation, okay? Because right now, you don't know that the mathematical step to solve this would be to take log base 5 of both sides. That sounds totally foreign right now. Be like, the mathematical step is using logarithms. But we don't know how to use logarithms yet. We're just using an observation. Eventually, we're going to get questions that this doesn't work, right? We could have something on our powers chart that doesn't work. Like, I could ask you to solve this. 5 to the x equals 42. Oh no. You go to your powers chart. 42 isn't in your power of 5. You look at any column. No column has both 5 and 42. We're stuck. But there's a way to figure this out with our calculator and get an exact answer. In fact, that answer, I hope you can see that it's going to be 2 point something. Because 5 squared is 25, and 5 cubed is 125. It's gotta be 2 point something. And we're gonna figure out how to do that on our calculator. Right now, all you could do is guess and check. You could try 5 to the power of 2.5 and see how close it is. And you find out it's too much. And eventually you'd be like, ooh, I'm getting closer and closer and closer and closer. And you're guessing and checking, and it'll be getting closer and closer to 42 until you're like, I'm happy that that's close enough. Try it right now. If we go to our calculator and we do 5 to the exponent of 2.32234, how close is that? 41.99999. Oh, so close. Maybe it should be a little bit more. 5.2. Oops.
Did you memorize that number?
No, I use my calculator with logarithms because I know how to use them. We're going to learn how to use them. But right now, I'm pretending I'm just guessing and checking. 2.322344. I want it a little bit bigger. I'm going to try a 3. Oh, not big enough. But it's closer. See how I got a 0.7? So I'm going to maybe make it a 6. Oh, that's even closer. Maybe it could be a 7. Or an 8. 8's too much. 7 is still good, but 8 was too much. So now I could do 7, 5. Oh, too much. And 7, 3. Oh, we're getting too entranced by this. 7, 3 is still too much. 7, 2. We could get decimals forever. Oh, 2 is too much. 7, 1. 7, 1 is too much. So now, I'm going to try 0, 5. 0, 5 is too little. 0, 8. Okay. This is so much fun, isn't it? You could, like now you could just spend your whole afternoon getting more and more decimal places. Well, that's too much. See, you guys are totally out of 5. Oh, we're so close.
You got a 2 at the end.
We're so close. You think it's a 6? Okay, we can't stop, right?
Oh, wait.
Okay.
There we go.
Whew. And it's actually not, like, it stopped at 42, because the calculator has so many zeros that it's, like, close enough, but it's actually not exactly that number. We'd have to keep, if we had a more powerful computer, we could do this for days. Just get closer and closer and closer. There was something disturbingly fun about doing that. I don't know what it was, but it just like, I don't know, I had a feeling of accomplishment. All right, questions to circle on this one. 9 and 10. So we're going to get to these questions eventually that we can't do that way. And we're going to learn about doing something like log base 5 of 42 and getting that number from that. So we're going to learn about those in a bit. But first, we're doing exponents. And we're starting off with just being able to guess and check and use technology.